So this problem is a cylindrical specimen of a brass alloy 7.5 millimeter in diameter and 90 millimeter long is pulled in tension with a force of 6000 Newton. The force is subsequently released. The tensile stress strain behavior for this alloy is shown in figure 6.12. So compute the final length of the specimen at this time. And the compute in part B, compute the final specimen length when the load is increased to 16,500 Newton and then released. So in this question, then we have to find the final length of the specimen in part A. So the final length of this specimen we can find if we know the change in length. So the change in length we can find from the strain. It is a brass specimen, so we can find the stress, and from the Hooke's law we can find the strain value, but actually we don't know whether the Hooke's law will apply or not. So we need to look at the figure 6.12. so let's look at what is the figure 6.12. okay, let me show the figure 6.12 here. So this is figure 6.12. Maybe I'll make it a little bit bigger. Okay, so in this figure 6.12 there are two curves. Okay, so this one is the full curve and this curve only shows the elastic region. So in this case you can see that the elastic region is somewhere for the stress level of about 250 megapascal. So if the value of the stress will be within this range, it will be in the elastic range, and if you will release that load, though, the specimen will come back to its original length. So let's find what is the value of stress in part A first. So part A, stress is equal to force is 6000 Newton divided by the area, because it is a cylindrical specimen with a diameter of 7.5 millimeter. So its area will be pi divided by 4 times 7.5 millimeter. So 7.5 millimeter is 0.0075 meter. So square. So if you will calculate it, this will be 136 megapascal. So if you see this 136 megapascal stress, you can see that it is in the elastic range. Yeah, so this is the scale of stress in megapascal. This is in the elastic range. So in this case, since the stress is here in the elastic range, so we can say that after we will release the stress, there will be no final change in the length. So no final change. So the final length will be 90 millimeter. Okay, 90 millimeter. So whatever the change will happen as a result of the stress, by the removal of the stress, the specimen will come back to its original length. Okay, so this was part A. Part B is compute the final specimen when the load is increased to 16,500 Newton. So the load is proportionately increased, so that the stress will also increase. So from the previous answer we can estimate the stress. So you can calculate it like this. If it is 136 megapascal previously, so the load was 6000, the current load is now 16500. So you take a proportion of that, so then it will be, in this case now it is more than double. Okay, 373 megapascal. So the stress has been appreciably increased. So now this 373 megapascal stress is outside of the elastic range. It is in the plastic range. So 373 will be somewhere here. So if you draw a horizontal line over here, let me draw it. Shape horizontal line. Okay, so this is the approximate horizontal line. Let's check it is horizontal. It's little bit inclined, so I make it, yeah, so it looks like horizontal. So it's 373. So 373 value will be somewhere here, and its corresponding strain will be this one. So to check the strain value, I draw a vertical line. So this vertical line intersects the strain axis at 0.1. Okay, so this 0.1 is the total strain. So total strain is 0.1. Actually, total strain is equal to the elastic strain plus plastic strain. So in this case, total strain is 0.1, and then we need to find the plastic strain from this equation. Elastic strain is given by this figure over here. And here you can see that this is the curve, stress strain curve in the elastic region, and then you can see that a line from the yield strength has been drawn parallel to the initial slope of the line, and it intersects the strain at a value of, so you can estimate this value is 0.002. So because this is 0.005, so each line of is about 0.001, so it is 0.002. So total strain is 0.1 and the elastic strain is 0.002. So what will be the plastic strain? So the plastic strain will be equal to 0.01 minus 0.002. So therefore you can say that the plastic strain epsilon plastic is equal to 0.098. So this will be the strain that will remain in the specimen after the release of the load. So the new length of the specimen will be then the original length, which is 90 millimeter times 1 plus 0.098. So it will be equal to 98.82 millimeter. So I think this answer is wrong. So the correct answer will be 98.82 millimeter. Remember that this is the same formula as the formula for engineering strain. Epsilon is equal to change in length over original length. So if you can write it like this: epsilon L naught and delta L is equal to new length minus the original length. So if you rearrange this equation, so you can write it, we can write it like Li is equal to L naught into 1 plus epsilon. So we use this form of the strain equation to calculate this.